6.3, number 13. So this is if $2,500 is deposited at the end of each quarter in an account that earns 5% compounding quarterly, after how many quarters will the account contain $80,000? So this one's a little different than the other one. Here, what's not known is the number of periods. So we have other information, but this is an ordinary annuity because we have the end of each quarter and we have compounding quarterly. So the information we start with is $2,500 payments. End of each quarter. So again, end is ordinary. And the quarter tells us that we have compounding of 4 per year. And our interest rate is 5%. And the future value is 80,000. And what we're looking for is the number of payment periods. So that's what we're trying to find. Okay, we need the period interest rate. So our interest, again, convert this to a decimal. And so then to find the period interest, that is our interest rate divided by 4, so 0.0125. Okay, this is an ordinary annuity, so the formula is going to be the future value equals the payment and then times the growth factor. Times I, the n minus 1, divided by I. Okay, and so we're trying to find what n is. We know what I is, we know what the payment is, and we know what the future value is. So this is going to involve using a logarithm to get access to that power. Okay. A couple ways to do it. I'm going to just do this algebraically and solve for n and then plug in, but you could also plug in the numbers and do some of the computation immediately. You'll end up at the same result down here. So fact, maybe, yeah, I'll be rewriting it. Okay, so the first step is divide by r to have that cancel. So you get S over R, and then that equals stuff in the growth factor. The next step is going to be to move this, multiply through by I to have that cancel. So you're going to move I up here. And so you're going to have future value divided by payment times the interest, the period interest rate. So and next you're going to add 1 to both sides to have these cancel, and then that gives, what that ends up with is you then have this expression by itself, and so now you can access the n by taking a logarithm. So the key step now is to take the natural log of both sides, and because you have 1 plus I, 1 plus the interest raised to the n, that allows you, and it's inside the logarithm, that allows you to multiply this exponent times the result of the log. So you end up here. Okay, and so now you have n by itself. I mean, it's multiplied by a factor here. Important to realize this is now a number, so you can just divide through by it. So it'll cancel. And so the expression you're left with is the number of periods equals the result of dividing these two numbers. You can also use logarithmic properties to perhaps simplify this. I'm not going to choose to do that right now, but that is a possibility. At this stage, I'm just going to plug in. So what we have is our future value, that's 80,000, divided by our payment, 2,500. Times our period interest, which was 0.0125 plus 1 divided by natural log 1 plus the period interest. Okay, so now we go about computing this. So 80,000 divided by 2,500 is 32. So we have ln 32 times 0.0125 plus 1 over ln 1.0125. 32 times 0.125 is going to be 0.4. So this is going to be ln 0.4 plus 1 over ln 1.0125. So this is 1.4 in there. So ln of 1.4, so you have 0.3364 divided by 0.0124. When you're doing this, it's probably better, if you can, to just divide the two expressions, because you need to store and keep all these decimals to get this right. So all right, and so you do the computation, you get 27.08. Now, this is asking for how many quarters you need to compound, and you can't have a decimal here. So this needs to be rounded. And if you round down, which is normally what you would do, you're actually going to end up short of 80,000 because you don't have quite enough compounding. So you have to round up. So your final answer is actually 28 quarters. Are needed to have, so you have 28 payments of $2,500 to grow until you get to the desired future value of 80,000.